Hi, so this will be a quick video on some visualization and also brainstorming about what we can actually do with this data set that we've collected before the COVID-19 hit. So actually we have a couple of images that were acquired in a very similar way, so we can do some comparisons there. But I've already had some interesting ideas about how we could compare this sample data set from a healthy participant with some atlas measurements which were published in this paper that I linked in our Teams folder. Okay, so just to motivate what's going on here, let me go and switch back to my terminal where I have access to the data sets that we have here. And so let me just show you one of the things that I created, managed to knock together by hacking around a little bit to give you an idea of the kinds of things you could be playing around with in the next few weeks. Obviously, we not just want to make eye candy, but we also want to do some quantitation and think about stuff. But there's a sort of a whole richness of ideas in there. Okay, I'm just going to use a command here to play a little video file that I've created. And so this probably runs a little bit fast. So let me just play it again a couple more times. So this is a little movie, a sequence of images of a 3D model that was constructed from the MR angiograms that we collected on this one person. Okay, so there's a couple of steps that that I did in order to arrive at this final visualization. The other thing to note is obviously it's not the cleanest image you've ever seen, but you can see that by rotating around this object in 3D, you can visualize, you can understand visually much better what's going on in this structure here. Okay, so let me just stop that here. It's a little movie file. I used a collection of tools which are all freely available, so not MATLAB in this particular case, but a bunch of other stuff. In particular, there's a software library which people in the biomedical imaging world use, which is called the Vascular Modeling Toolkit, VMTK. It looks like you have to pay for it, but actually this is just an additional tool that they build around it. The tool itself, the toolkit, is written in Python and a bunch of other stuff, and it's freely available. So you can go to the download button and install this on your machine. Because I've done this just sort of by warning a little bit. So there are some binary install packages which should work on Windows and also Mac OS, but it turns out for the latest version of Mac OS, I basically picked one of those and it didn't really work, so I had to install it from source, which is a little bit of a pain, and you might not want to brave that, but you could try and have a go. I know a couple of you are working on Windows anyway, installing these things and see whether you can make some headway there. If not, don't worry. I just wanted to let you know that these things are available, and maybe what we could do is, for the things that you have a hard time running on your computers in your various locations, I can run that code for you, create the intermediate files, and punch out a bunch of numbers, and then we can work from that. Okay, so the nice thing about this here as well is that there's a bunch of tutorials and getting started things, and all of the things I want to show you in the next couple of minutes is actually derived from some of those tutorials and walkthroughs. So I haven't even dug into this very deeply, but there's sort of a couple of things that we can that you can do with this toolkit without going back all the way to the maths that might be quite useful for us. In particular, there's different methods of segmenting out these blood vessels from medical images. So there's a couple of examples there, just to give you an idea. So, clinicians might use this kind of stuff to look for aneurysms and places where blood vessels are thicker than they should be. There's center lines where we can actually, if you look at this in a bit more detail, if you imagine having a vascular tree, which looks really nice and smooth here, and ours look a bit more messy, you can identify the path that goes through the center of these structures, and that allows you to actually visualize the tree in which this thing is organized. So that might be really useful for us as well. And you can use that information to then do other things like figure out what is the vessel thickness at various points. So there's a whole bunch of tools that you can look for, branching patterns and so on. Probably some of this stuff is going to be a little bit too advanced for us, but just to show you that all of this stuff is there and we don't really have to reinvent the wheel. Okay, so that's there. So the website for that is vmtkvascularmodelingtoolkit.org, and you can just go there and play around a little bit. So I've prepared some of those files already. So let me just go over here, do this. So the first place I want to go to is this angio folder, which is linked here in this location. So I'm going to use a command called pushd, which is the same as change directory, but it remembers where you were before. So it's easier to come back to the location where you currently are. So there's a bunch of files in there. Some of them you will recognize because you have access to them already. Actually, they should now all be in the Teams folder if you've synced up, but some of them will make sense to you and some of them won't. Okay, so just to show you what these tools look like. So they're basically written like little Unix commands. There's a whole collection of them if you install this program properly. There's an image viewer, so which feels a little bit like sort of the FSL viewing tools, and a bunch of little command line tools that you can stitch together to build up these pipelines. Okay, so I'm not saying you should go away and learn this whole new tool. I'm just saying these are some of the things that are available to us and we can play around with. So when going ahead, you should think about what are some of the ideas that you would like to explore. Okay, and maybe you even have a very practical idea of how you would maybe make the measurement, how could you get the diameter of a blood vessel, and so on and so forth. And then together we can discuss how we could actually achieve this in practice, because it might be quite tricky for you to figure out what actual steps are required. But I think some of these things should be quite doable. Okay, so I'm just going to copy and paste this command which I've prepared earlier. I'm going to hit the viewer button, and so what I'm actually running is I'm using an algorithm called the marching cubes algorithm, which you can look up on Wikipedia. It's sort of a little bit complicated, but it allows you to take a volumetric image, so one that's made from voxels and pixels, and turn it into a surface representation using triangles and polygons, which are really good for doing certain kinds of analysis, right? So think about, if you don't know exactly what that means, think about the difference between having, say, a 2D photograph, which is represented on the computer as a bunch of pixels with intensities, and a vector graphics like a PDF file where lines are represented as geometric objects, okay? And there are very different ways of representing the data. We can talk a little bit more about this in a while. So this algorithm went through this very big image in 3D and reconstructed the surface representation of what's present here. So this is actually a 3D model that we can explore. It's upside down actually, right? So let me turn this around with my slightly clunky mouse. So all the vessels that are pointing upwards are pointing into the brain. So on this side here, on the right-hand side, that's the front of the head, and this is the back, and maybe you can sort of see a hint of the blood vessel patterns that are going on here. We don't have pictures of the internal carotids coming up. Sort of cut off, but if I look at it from this particular aspect, you can see that there is sort of this thing which looks like it might be connected actually. It's a circle of Willis at the bottom here. Okay. So the idea would be to try and make sense of these tree-like structures, clean them up a little bit with various pictures, with various algorithms and then turn that information into something useful. Okay, so just to bring home that point about what is the difference between a pixelated image and this tessellated or triangle representation. So if I switch the surface representation, which I can do with a letter W, you can see what's going on here. Okay, so this is actually a mesh that's made up of little triangles. So we're not talking about pixels anymore. So here's the actual mesh without the surfaces. If I go back, it renders it in the slightly smooth version. Okay, and so this is a complete 3D model of everything that had a particularly high intensity in these images. All right, so I'm going to stop this little video here to keep them short. In the next video, I want to look back at this other data set that we have, which is actually derived from the paper, which is the atlas. And one thing we could play around with is to make a similar representation for of the atlas data set, which is actually the average over many brains, and compare it to this data set from one particular person.